ECT scan tool testing, page 10. So we're going to start talking about testing this engine coolant temp sensor. There's a lot of fundamentals in here that you want to pay attention to. Really important for all thermistors. But we're going to focus on the ECT. Number one, I'm trying to give you some quick tests that you can do. And the first thing you can do as far as checking an engine coolant temperature sensor and whether or not it's reporting an accurate signal would be to put the scanner on the car. Before you start the car, let's say the customer brought the car in the night before with a check engine light complaint or some kind of running problem. One of the things that you don't want to do is to test drive the car first. And that's what we're always taught, test drive the car first. Take this scanner out with you, because as soon as you start the car and maybe go for a quick test drive, you've blown a window of opportunity that you can do some checks on. And with the engine cold, sitting overnight, you can compare your engine coolant temperature and your intake air temperature sensor to each other on the scan tool. They should be the same temperature. If you think about it, you got two different thermistors, one reading outside air, one reading engine coolant temperature. They should be the same temperature. You got a tolerance of within 5 degrees of each other, but very, very nice quick test for accuracy of the engine coolant temp sensor. Number two, compare the engine temperature to scan data temperature. So infrared temp gun. That's what I use here. Here's my infrared temp gun to do that. Some of you guys will use a digital pyrometer, but they take way too long to get an accurate reading on. I don't like those. They sell them with multimeters. You might have gotten one with your multimeter. I don't like those. You need to have an infrared temp gun. And what I found is my temp gun that I use reads within 1 or 2 degrees of the coolant temp sensor. The one we have in the tool room here, you got to be careful with because it's about 10 degrees off. The one I use is made by Raytek. Raytek is the manufacturer. It was about $100, and I've had it for 15 years and have not had one problem with it. So just a little heads up on what I'm using. Number three, warm up the engine, know the coolant temp when the cooling fans turn on, and I may or may not do this. Now, I guess I should state here that these are not necessarily in any particular order except for number one, if the engine's cold. If the engine's not cold, you can't do number one. As far as number three goes, I'm not really going to be concerned about that unless the customer complaint is overheating. So then we're focused on that, when does the cooling fan turn on type thing. Something to consider, a little bit off topic, but as far as overheating conditions go, and a lot of guys miss this, they don't pay attention to detail, and I don't understand why, but customer complaint is overheating and they may not let the car sit in the shop. One thing that can happen, let's say you have a cooling fan problem and you're not thinking about what's causing the overheat. You go for a test drive and you go on this long test drive waiting for this car to overheat. It never overheats. And the reason it doesn't overheat is you're not sitting in traffic. You got constant airflow across the radiator. You don't need the cooling fan. That's the purpose of an electric cooling fan. So you bring the car in the shop, let it run. Let it sit there and run. No airflow across the rad. See if the cooling fan turns on. That's like the first thing I do when I have a customer complain of an overheat. I don't drive it. I just start it up, let it run. Keeping my eye on it, of course. We don't want to let that thing sit there and run too hot. Number four, for intermittence, this is for any sensor fault. When you have an intermittent, it's wiggle the wiring, wiggle the sensor, watch for a change. That should be pretty much common sense, that part. But when you do this wiggling test, I'm going to teach you what you want to be looking for. So 5 and 6 on this list, we're going to look at data on the scan tool. The next page, I've thrown in voltmeter checks. And it can be your scope too, because maybe you have the scope out. But voltmeter's fine for the engine coolant temp sensor. Scan tool wiring tests. Scan tool wiring tests. So we're not using a voltmeter. We're just using our scan data. Now, this is going to depend on the car that you're working on whether or not you're going to see ECT voltage or ECT degree Fahrenheit, because this would be your two data parameters or data PIDs that you will see. You may not have both of them. You may only have one. I've had cars that only give you the ECT degree Fahrenheit. Myself, I would rather see the ECT voltage because the degree Fahrenheit is processed based on the voltage. Now, everything you look at on the scan tool is processed information. However, the ECT degree Fahrenheit is that lookup table number, and that guy can be substituted. So I want to share that with you. If you have an ECT sensor that the signal voltage is fixed at 0, so you're looking on the scanner and you see a 0 volt signal on the ECT. You don't have to go crazy and pull a wiring diagram and get your voltmeter out and start doing wiring checks. All you need to do is reach down and unplug the sensor. If you unplug that sensor and your scan data goes to 5 volts when you unplug the sensor, you're done. What do you need? Your sensor's shorted out. Do you have to check the sensor ground wire? No, because if you had a bad ground wire, what would you be reading all the time? 5. Think about circuit design. What's the computer do? It's sending 5 volts through a current limiting resistor through the thermistor on its way to ground. This is your sensor. This is inside the computer. The sensor's out here. Inside the computer, there's a voltage monitoring or sensing circuit between the two. If you have 0 volts all the time and you reach down and unplug this ECT and your scanner now reads 5, that tells you that the signal wire integrity and the computer is good. And the reason you were reading 0 all the time is this thermistor shorted out and it's pulling it straight to ground. It's the only cause. So ECT signal should rise to near 5 volts when you do that test. What if the scan data only gave you the degree Fahrenheit number? This is where you need to know temperature and voltage. In your head, remember this too, because you're going to see this on an ASE test. When you see high voltage, is the engine hot or cold? So you have to have this perspective first on a thermistor. High voltage on a thermistor, ECT, is going to be what? Hot or cold? Very good. It's cold. High voltage is cold. Okay? So if you know that when you unplug an ECT, that it should be a cold temperature, then you can kind of get an idea of what we should be looking at here. And generally speaking, 5 volts on an ECT is equal to negative 40 degrees Fahrenheit. And that's pretty standard across the board, that number. So if you had a vehicle that was fixed at 0 volts, you might have something like 350 degrees on the data display. And that's going to be different for every car. 0 volts is going to be anywhere from, I've seen them as low as 270 to as high as 350 degrees. Somewhere in that range that 0 volts is. If you disconnect that, what do we want to see this number drop to? I want to see that go to minus 40. If that goes to minus 40, how's your wiring? That's the point of this. And then your focus is what? Right on the sensor. And guys, listen, all we have is a scanner in hand. And then we're just some common knowledge of the circuit, and we're just reaching down and unplugging it. Okay? Warning to you guys, though, is this right here. Substituted values. This is one of our supporting sections up here on what we're talking about right now. Section 11, I'm calling this support for all these other ones. I'm going to take you there real quick. I'm not going to go through this whole thing right now. I want to take you to one picture. It's this one right here. And this was a vehicle with an ECT that we were just playing around with. And what we did on this engine was we unplugged the engine coolant temp sensor. So from what I've given you so far, what would be my ECT voltage reading with the sensor unplugged pretty much on any car, on any thermistor, across the board, every year, every make, every model? It's 5 volts. Because we're not giving that internal resistor a place for voltage to drop. You've unplugged the sensor. 5 volts is the source, goes across the current limiting resistor on its way out, but there's no drop because there's no current flow. 5 volts on a thermistor is what you're going to read. 5 volts, we know that 5 volts from what we just talked about would be a cold number somewhere around negative 40 degrees. Look at this number. I disconnected the engine coolant temp sensor and look at the number I'm reading. 104 degrees Fahrenheit. Same car, 2 different methods of communication. We have an OEM format, that's original equipment manufacturer, that's our factory data display, where you have to enter year, make, model, engine, put the right key, the right chip in so we can communicate with the car. There's a second way to talk to the car, and that's no year, no make, no model, global, OBD2, generic, and a $60 scan tool will communicate this way. Same car, same picture, same conditions. Look at the coolant temp sensor reading. Isn't that what we expected to see with the sensor unplugged? It's minus 40. Well, what's up with that? It just throws a monkey wrench in the picture, and it's a substituted value is what it is. There's a trouble code in memory from the engine coolant temp sensor being unplugged. The computer knows there's a problem with that sensor, and it throws a number in that's more usable for its running operating curve based on run timer, intake air temperature. Does that make sense?
So that number can vary then?
Yes, that number will vary. And it can actually change as the engine's warming up. So imagine that. You are only dealing with maybe this, and you have a dead sensor, and as you're running the car, you see this temperature warming up. You're like, why is it set to code? And you go out and check it under the hood, it's fixed at 5 volts. You're having trouble absorbing that. It's conflicting information. What else happens during this condition? What else do you think is happening? When does the computer substitute a value? And when is the only time the computer will substitute a value? That sensor has to be dead right now. The term for that is called a hard fault. A hard fault is one that's occurring right now. A soft fault is an intermittent code. It's not happening right now. When will or may the computer substitute a value on the scan tool? And when is the only time? It just doesn't do it randomly. You don't get voltage substitutions or degree Fahrenheit substitutions with a working sensor. It's dead. 5 volts or 0 volts is a dead sensor on the CCT, right? We see 0, computer knows it's dead. We see 5, computer knows it's dead. If that sensor fails in range, like that Saturn I gave you guys an example of, where it's 30 degrees off, are you going to get a substituted value for that? No, because there's no trouble code for it. Substituted values, in my experience, are always accompanied with a hard fault. Does that make sense? So how do you know when you can rely on the data and when that data may be substituted is go look at the trouble codes, current codes. Is it happening right now? If it is, you may have to deal with a substituted value that's going to throw you off. Don't let it throw you off. Okay? The computer will do that. Why in the OBD2 global mode is it reading accurately? They weren't allowed to substitute values in that section. So maybe something good the government did for us for once. This mandate right here, I kind of like that. Show me what it is, don't throw the value in there. OBD2. So another way you can tell if it's substituted or not would be check it in both modes. So we'll come back to substituted values. That's not the only time you're going to see one, but that's why I mentioned it here in this. If you're doing this test, or if the signal's fixed at 0 volts and you're unplugging it, you expect it to go to 5, or you expect your ECT degree Fahrenheit to drop to -40. Do you understand the footnote now? It might not drop to -40. In fact, it might show -40 for about a half a second, and then all of a sudden it shows 104 degrees. And that means that it saw it, flagged it, and basically is looking away from it, throwing in a valve. This is one of the reasons why technicians can get in trouble, because they take the data at face value and not think about what could be happening here. I've heard the argument with Ford on early models why they didn't want to give their technicians the data, and this was why. They thought we weren't smart enough, I guess. I don't know. I don't know if that's true or not. But. Okay, signal fixed at 5. What do? Again, we're not using a multimeter. I'm just trying to show you a way that we can do this without a multimeter. If our signal's fixed at 5 volts, what do we know about the circuit? Is it open or shorted? It's open. Remember, the computer source is 5 volt out, right? And watches what it's sending out. So if your signal voltage is fixed at 5, looking on the scan tool, when we see ECT volts and it's at 5, what can we do if we don't have a multimeter? Go down to the sensor, unplug it, and jump the 2 pins together. Are we okay on every thermistor circuit doing this step? There's a lot of confusion in the field as to, wait a minute, you're going to damage the computer, and the answer is you are not. The circuit design, again, goes through an internal current limiting resistor to an outside resistor to ground. Let's talk about the normal operation here for a second. 5 volts is the source inside, so this is maintained at 5. That never changes. On a operating system, you may see in this signal wire right here, in the signal wire, you can read maybe 4.5 volts all the way down to as low as maybe 0.4 of a volt. So it pulls, the sensor itself pulls that 5 volt signal all the way down to almost ground when it's hot. Some Ford systems, the cooling fan doesn't turn on until it hits about 0.4 of a volt. Then the cooling fan turns on. So here's my point with that. Am I going to cause an increase in current flow more than what the sensor is going to do itself by unplugging that and running a jumper and just simply pulling it all the way down to 0 volts? Is that going to cause damage? No, the sensor's designed to be pulled to ground. That's what this resistor does. If that resistor wasn't there, would we want to do this? No, we're not going to do that on some of these other sensors. We're not going to jump the 5 volt reference to ground ever on any other type of sensor except the thermistor. Are we safe in doing this procedure? Absolutely. So what you're doing, if you're fixed at 5 volts on the scan tool, ECT's at 5 volts on the scanner. You reach down, disconnect the ECT, jump 2 pins together, and this drops to 0 volts. You're done. How's your signal wire? How's your ground wire? All right, what if it stays at 5 volts? Is it the ground that's open, or is it the signal that's open? You don't know. So now what do you need to finish the process? We don't need a diagram yet. We need a voltmeter. We need to do some voltage measurements. So what I'm showing you first, what can we do with the scan tool? This is scan tool testing. What can we do? Can we figure out where our problem's at with the scanner? And most of the time when you have a fixed 5 or fixed 0 signal, it's the thermistor that has failed. So you can have wiring problems too, but usually the wiring problems are right there at the sensor or the connector. What if it's an intermittent code? Can we look at our ECT data parameters, whether it be our ECT voltage or the ECT degree Fahrenheit, and wiggle the connector and just watch it? Should you get any changes in a thermistor circuit by wiggling the connector? Should it stay steady the whole time? Should stay steady the whole time. So if you have an intermittent ECT code, you might not want to do step 3 before you do step 4. That's why these weren't really meant to be in order. Because if you're going to reach into the engine and start wiggling the harness, wouldn't you rather the engine be cold than be like 300 degrees? Granted, the engines aren't that hot, but it just feels like that sometimes. Just think a little bit, okay? Intermittent trouble codes. Last part on the scan tool. I will use the ECT data parameter to tell me whether or not my thermostat's operating properly. And the key with this is to test drive the car with a constant airflow across the rack. Whether it be you live near a highway, if your shop's near a highway, you're in business. Mine wasn't. I lived, though, in a section where there was a nice 4 or 5 mile run with no stop signs, no traffic lights, that I could get a constant airflow at 25 miles an hour and I could watch my coolant temperature. And I wanted to make sure that it stayed above 185, 190 degrees. If it stays above that temperature, how's your thermostat? The purpose of the thermostat is when we reach that, say, 190 degree temperature, the thermostat's going to close, which keeps that cold coolant that's in the rad from going into the engine. We maintain that hot temperature. That thermostat's constantly opening and closing as you're driving that car at highway speeds. Highway speeds with constant airflow, your thermostat is constantly opening and closing. Blending cold and hot temperatures with the motor. So it's the best time to check for a thermostat is watch your ECT temperature. and make sure it stays hot. And then, of course, another note, we've talked about this, is a stuck open thermostat can cause poor gas mileage from extended open loop operation. And it'll set a trouble code on some of the newer systems, so that's money right there. The voltmeter checks on page 11 are really the same kind of thought process. If you understand how the circuit works, well, I think we do now. 5 volt from the regulator through a current limiting resistor on its way out to another variable resistor. We have that picture in our head how the circuit works. Checking them with a voltmeter is no different than what we just did with the scan tool. Some cars, you need to understand that the scan tool is not available. There's a lot of cars still on the road that have no data parameters. Take older Hondas or older Fords. Did not provide scan data. There was no way you could even connect to it. Some of those older Hondas, all you had was an LED light on the computer and you could get trouble codes out of it, but you certainly weren't hooking up a scan tool to it. Maybe a factory scan tool, but when you work in the aftermarket like we do, you have 20 different car lines. You're not going to have 20 different manufacturer scan tools. So you have to have a way to do it. So the idea here would be 2 things. Even if you can use the scan tool and you do have data, they're still required at times some voltmeter checks. Like I said, we're fixed at 5 volts, we unplug the ECT and we jump the 2 pins and it stays at 5, we have to do voltmeter checks. Or if there's no scan data available, that's all you have. That's what you got to do. Okay, key on engine off or key on engine run. That would be number 1. You need the circuit to be alive. The circuit's not alive with the key off. Turn the key on, do some checks. When would you want to do it running? That would depend on what you're trying to do. If you're trying to get a temperature reading when the cooling fans come on, you might want it running. I think for the most part, most of this is going to be done with just the key on. You don't need the car running. The circuit's alive and active with the key on. If you want to look at the range and different temperatures, different voltages, then you'd want to have the car running. Okay, negative lead to a known good ground, positive lead to each of the wires individually. Something you want to remember again, this should sound familiar. Down here, we'll just start with this. We're doing a ground to ground voltage drop test with the circuit plugged in, back probing. ECT ground voltage should be, as with other sensor grounds, less than what? 100 millivolts. Less than 100 millivolts. If you read higher voltage on that sensor ground, you have a bad sensor ground. Sensor grounds, guys, are grounded to the computer, and then the computer grounds the next terminal. So when you're talking about this circuit, this is your sensor ground wire down here. This is your signal wire. Sensor ground comes back to the computer. Okay? This ground would be inside the board. So that whole ground path that goes all over the place inside of the circuit board, that's going to ground to that. And then from there, these guys come out at some point maybe in 2 different locations, and these are called power grounds. Power grounds ground the whole board. Sensor grounds go back to the board to get a ground. So ultimately, where are sensor grounds getting their ground from? The block. You got a bad sensor ground, you may have a bad block ground. We may have a bad power ground. But they do get it from the board. Although you could have a wiring problem in the ground wire itself. In any case, less than 100 millivolts is where we want to be for a sensor ground. Sensor signal wire, measure the signal and compare to the engine temperature using a chart. Now, where do we find these charts? Mitchell, unfortunately, does not provide, it's actually not Mitchell's fault, it's the manufacturer's fault. The manufacturer typically does not provide degree Fahrenheit to voltage charts. What they provide for you is degree Fahrenheit to resistance charts. And that sucks. And the reason that sucks is if you understand where some of these ECT sensors live, to disconnect the sensor and get your ohm meter to reach the 2 pins of the ECT is impossible on probably half of the cars out there. So in other words, you can't get your leads where that ECT lives, so what do you have to do? What's the manufacturer recommend you do? disconnect the ECT, remove it from the engine, and measure its resistance while it's in your hand. What if that sensor has nothing to do with your problem that you have, but it's step one of their diagnostic flow chart? I mean, are you kidding me? Give me the voltage number that it should be, and then what I can do, let's say this sensor lives down here in a really bad spot, but I can access the wiring up here. Yes, I know, we don't want to poke a hole in a wire. In this scenario, guess what I'm doing? I'm poking a hole in that freaking wire, because if I do the other check, it's going to take me an hour to do it. And that might not even be the problem. I'm just trying to get a baseline reading on this coolant sensor. That's all I'm trying to do. You guys with me? So where do we get a voltage to temperature chart? And the answer is this right here. That tool right there. Little Snap-on plug. It's got every car, year, make, and model, engine coolant temperature to degree Fahrenheit chart. That's what you're paying for when you buy this tool. Vantage Pro is a very nice scope. The old Vantage was not a scope at all, but it was this database that made this tool so powerful. If you know that at 200 degrees, that your engine coolant temperature should be reading 1.5 volts, how easy is it to put a voltmeter right here, and you read 1.5 volts on your voltmeter, and you know with your infrared temp gun that you have 200 degrees of engine temperature, you're done, move on down the line, your coolant sensor's fine. One of the things you guys have to learn how to do is doing this type of stuff. You have a list of checks you want to do, and you want to start checking them off real quick. When you don't know what the problem is, how's your coolant sensor? How's your TPS? How's your MAP sensor? How's your mass airflow? What's your fuel pressure? What's your spark look like? So we go down the line, and you see how fast we're able to address this coolant sensor. Is it working? Is it not working? 1.5 volts, infrared temp gun, very fast. Keep this in mind, that what we want to see with a hot, and I'm just giving you some typical numbers, and this is for you guys that maybe don't have this tool or are not going to buy it. Typical hot engine reading on a coolant sensor is around 0.5 volt to 1.5 volts, and cold engine 2.5 to 4.5, and that's going to depend on time of year and where you live. You know, do you live in the mountains where you got sub-zero temperatures a lot? Then your temperature when you first turn the key on in those cars is going to be a lot different than somebody who lives down south. Okay, just some ballpark numbers. Let's say you have here's a scenario. You have a car that's flooded, and you're pretty sure that your coolant sensor is reading too cold on the hot engine. It's caused it to flood. If you connect to a coolant sensor and that engine's 200 degrees and you see 4 volts, I'm telling you, on any car, that's a bad number. 4 volts on a hot engine, right? So that's why I'm giving you these ballparks. You have an engine that you think might be flooding out from a bad coolant sensor, and you see 4 volts on a hot engine. Stay where you're at. You found your problem. Now go confirm it and find yourself a chart. That's going to be your problem. Your coolant sensor's messed up. All right, so what do we do with these two? Signal fixed at 5, signal fixed at 0. Very, very similar as with the scan tool. I have some figures I want to show you. Signal fixed at 5. Let's go to figure 2. I have check your sensor ground. If your sensor ground's good, either the thermistor or the connector's bad. So figure 2. Figure 2. Signal fixed at 5. So we're using our voltmeter and we're checking our signal and we're reading 5 volts on the signal wire. Okay? The next thing you want to do is check your sensor ground. If you read 5 volts on the sensor ground, you do not have a bad thermistor. What do you have? A bad ground. That 5 volts is going to go this way. It's going to be 5 here, 5 all the way down. It never drops across the resistor because there's no current flow, so there's no voltage drop, and so your ground voltage will read 5 volts too. If you go to your coolant sensor and you read 5 volts on that sensor, right off the bat, what do you have? Bad ground, period. Right? So that's what you want to do. If you are reading 5 volts on the signal all the time and you check your ground, again, this is plugged in, back probing, you're 0 volts on the ground, you're done. What do you got? You got a bad thermistor. That sensor is open, or the connector's bad. You know, maybe somebody was in there and spread the female pins of that connector, and that's going to be a visual inspection, tug on the wiring, make sure they're not broken. Connector or thermistor. Okay? And this is scan data signal fixed at 5 too. So there's another variable here. When we're doing this, I have, what are we doing? Voltmeter checks. Signal fixed at 5. The variable here is, well, where did you measure that signal at? If your scanner's reading 5 all the time and you come out to the sensor and you're reading 0 on the signal wire, you're going to have to go to the computer, read it there. You're reading 5. If you're reading 5 at the computer and 0 at the sensor, what do you have? An open in the signal wire. So another variable with that. Fixed at 5 volts. Open signal, open thermistor, open ground. Okay? Could you have a bad computer? It is possible. And that would be that if you, let's say this was connected and you came over here and you read 5 volts all the way back to the computer, then you have a sensor ground problem internal to the computer. When we were working on that Ford truck, you guys remember me having you check the sensor grounds repeatedly for our condition? I was worried about a bad ground on that truck, and that's why I kept having you check those. Okay, signal fixed at 0. What do we do? Disconnect the sensor, signal voltage jumps to 5, the sensor is shorted. If signal voltage remains at 0, there's either a short to ground or an open in the signal wire. We need to compare the two. What is this? Okay, that's 2B. Hold on a second. All right, I just messed up my my picture with my flow chart here. 2B, we talked about this one already. If the scan data shows 5, there's an open in the signal. That's figure 2B. That's this one right here. Still fixed at 5. Fixed at 0, you either have a shorted thermistor or a shorted signal wire. Sensor is shorted, or there's a short to ground or open in the signal wire. And that would be dependent on where you're measuring that on this open. This can be a little difficult. Try to hang with me here. Figure 3. So scan tool's reading 0 volts. You come out to the sensor and you're reading 0 volts. What do? How do you know it's this? Disconnect this. What should the scan tool do? We should read 5, right? If it stays at 0, this is most likely your cause. You can disconnect the computer, disconnect the sensor. You can put your ohm meter in here. What should we read with this disconnected on a good wire? With this side disconnected and this side disconnected, what should we read with an ohm meter? What's a good reading for this test? It's OL M ohms. If we read that, how's the wire? It's good. If we have any number other than that, you have a short to ground in that signal wire. If you reach down and disconnect this sensor, and this goes back to 5, what do you got? Or if you're using your voltmeter, and you have this T-pin on the harness side, and you're reading 0 volts, and you disconnect the sensor, and this goes from 0 volts to 5 volts, what do you have? Shorted thermistors causing that. So there should have been a couple more pictures here. I apologize for that. I had to modify that. I think 2 more pictures showing that this disconnected was the key. That's what we were doing here. Disconnect the sensor. And I think the only mistake I made maybe in this picture, it looks like, is in both of these pictures, this should be disconnected. Now, it would still need to be modified, because if this is disconnected, I needed to show this picture like this, and then showed it disconnected too. Let me do that for you again, just to make sure we're clear here. Fixed at 0 on the scanner, or fixed at 0 with a voltmeter. Your next step you would do, disconnect this. Disconnect the sensor. This should jump to 5. And this should jump to 5 if your thermistor was shorted. That's what it would look like. Same thing, computer at 0, scan or voltmeter at 0. You disconnect this sensor and it stays at 0. It is not a shorted thermistor. Your problem is right here. Sorry about that. I really screwed this picture up. You guys might want to change that. Well, you want me to draw the second one? I can do that. It's going to look like this. We've disconnected the sensor is the key. Scan tool still reading 0 inside the computer. And on the harness side, you're reading 0 here. This is most likely your cause. This would be plugged in. This is unplugged. And on this side over here, still dealing with a fixed 0 signal. We've disconnected the sensor. With the sensor disconnected, we're reading that. See the difference? So again, I apologize for leaving that out. Shorted thermistor in this case, that's what I have listed here, shorted thermistor. And then in this case, we have a shorted signal wire. This is plugged in and unplugged. So I should have had a second picture here to go along with my notes. I mean, you don't need it if you can visualize what I told you. The text is good. The text is accurate. Disconnect the sensor. Signal jumps to 5. Sensor shorted. If the signal remains at 0, short to ground, opening the signal, and that's going to depend on where. This opening the signal is going to depend on where you are measuring for that. And that would be the second one right here, addresses the opening the signal wire. Scan tool's reading 5, but at the sensor it's reading 0. Other than that, short to ground. This is every single thermistor on a car is done the same way.